안녕하세요. 반갑습니다. 저는 오늘 테크플러스 2013의 사회를 맡은 태인영입니다. 반갑습니다. 네, 오늘 첫 번째 세종대학교 무용과 서차영 교수님의 안무로 오프닝 주제 공연을 함께 보셨습니다. 아마 여러분들도 이렇게 무용을 보시면서 어떻게 인류가 진화해 왔고 또 어디로 가고 있는가 이런 생각을 잠시 하셨을 거라고 생각하는데요. 오늘 이 테크플러스에서는요, 이제 이 세계가 미래를 향해서 어떤 기술들을 개발하고 있고 그런 개발 과정에서 우리 인류가 어떻게 변하고 있는지 오늘 정말 다양한 분들을 모시고 실제로 그분들은 그런 기술을 만들면서 그 기술로서 많은 변화를 가져오고 계신 그런 산증인들입니다. 그분들의 이야기를 들으면서 우리는 또 어떤 상상을 할 수 있을지 한번 생각해 보시길 바라겠고요. 혹시 강연을 들으시다가 궁금하신 점이 있으시면 이따 오후에 저희가 질문을 받는 그런 시간도 마련되어 있으니까 다양하게 이렇게 어떻게 하면 나의 의견과 저 의견을 함께 접목시킬 수 있을지 생각해 보시기 바랍니다. 자, 첫 번째 특별 강연으로 나노 기술의 창시자이신 분을 모셨습니다. 여러분, 나노 기술이 어떤 기술인지 아시죠? 아시나요? 네. 나노, 정말 우리가 옛날에 생각했던 아주 작은 입자에서 정말 작게 쪼갠 그런 기술의 창시자라고 생각하시면 되겠습니다. 에릭 드렉슬러 씨의 특별 강연입니다. 강연 제목은 Creativity and Future Technology인데요. 이걸 해석해 보면 Creativity, 창의성과 우리의 미래 기술 이렇게 해석이 되겠습니다. 자, 동시 통역기 필요하신 분들은 착용해 주시고요. 한국어는 1번 채널, 영어는 2번 채널, 그리고 휴대폰 잠시 꺼두시는 것도 잊지 마시기 바랍니다. 자, 큰 박수로 강연 초청해 듣겠습니다.
Good morning. I would like to thank the organizers of this meeting for inviting me to return to Korea and to have the opportunity and the honor to speak with you this morning about what I believe will be some of the most important developments of the 21st century, developments in which I hope Korea will play a strong role with its background in science, technology, and vision for the future, which has been displayed with emotional depth here in the opening of this meeting. So, my topic is radical abundance, the prospect for a technology of production, of making the things of our world and our lives that is radically different from the technologies of the Industrial Revolution. A technology that can transform the material basis of human civilization, and with that, of course, the material basis for human creativity, because, to a great extent, what we can think about, and certainly what we can do, depends on what we can make. During the first million years of progress, the level of technology was stone, starting with crude, chipped choppers, through finer and finer control of stone, which provided the tools that people used to create works of art that even today strike us as beautiful, that have an emotional content, that tell us something about the lives and sensibilities of the people at that time. So, since earliest times, people have used tools to make art, and people have used tools to make the things that are used in everyday life. And with progress in metals, metalworking technology, the ability to make sheets of material on which one could make durable marks for later generations, people developed new forms of art and new ways of making the things of everyday life. If you look at this piece of ceramics, you can almost see the tool of the spinning potter's wheel and the shape of the hands, and the brush used to lay down the glaze. And yet this kind of technology, this application of technology, is not the heart. It is not the center of human progress. It is a fruit of human progress. It is not the branches. It is not the trunk of the tree. The trunk of the tree of human technology is the process, the growth process, is using tools to make not things that we use in everyday life, but tools to make better tools. And so our ancestors, starting from a technology of stone, learned to dig and use fire and make iron. And with iron, iron tools, iron hammer, iron anvil, iron tongs to hold the hot metal. And blacksmiths in those days, with these technologies, with these abilities, worked, and year by year, passing on to their apprentices and to future generations new techniques, new tools, better anvils with shapes for shaping iron in more useful forms, better tongs, mandrels, all of the components involved in a better metalworking technology. And people learned to make steel, and they learned to make finer things made of steel, and they learned to make clocks and machines, and eventually the machines that made possible the Industrial Revolution. Machines used to make machines, machines of greater precision, greater strength, greater speed. And those machines have taken us a very long way. People learned to build with yet better materials, greater precision, to organize society in ways that enabled complexity at unprecedented levels, to build machines of a scale that could take human beings out of our terrestrial world and into the broader world, to reach out to the moon and beyond. Today, there are products of human hands that have begun the long trip to the stars, falling endlessly into interstellar space. In the 1970s, I was part of this space technology area, studying at MIT in aerospace systems engineering. And while working there, I found myself with a curiosity about other areas of potential technology. And looking at biology, I saw that people were discovering molecular machines inside cells, machines that could take digital information, genetic information, use that information to direct the assembly of molecular components. Ribosomes can be viewed as numerically controlled machine tools for the construction of atomically precise nanoscale components. Enzymes, the components that make up the machinery that builds cells, that enable your muscles to work. And that vision of a molecular nanotechnology was part of a broad thrust. In addition to moving up and out into larger machines, people were moving down and in to the world of today's leading nanotechnology. People hear about nanotechnology. What is it? Often it's referred to, the term is used to describe materials with nanoscale parts, nanoscale particles. But the great nanotechnology in the world today, and one in which Korea is a leader. When I was here last, Samsung announced a key step that was in the lead of the world in making small features. The greatest nanotechnology is nanoelectronics. The technology of making wafers with chips to have billions of components, nanoscale electronic components in large arrays that work together at high frequencies, processing information in its smallest components, in bits. And this technology at the base of the information revolution, the post-industrial revolution, is driving change in the world on an unprecedented scale, and that technology is a nanotechnology. It has enabled a kind of creativity that is unprecedented, one based on building immensely complex patterns from the simplest parts, bits, pixels, bits of light and color. And from those, people have made what amount to new worlds. Worlds that are rich, worlds that contain other people through the internet, worlds that in some cases, even though they are not real, people nonetheless seem to move into them and live in them. We have certainly heard of some cases of people who spent a bit too much time and attention in virtual worlds. But this kind of creation, many different kinds of worlds for many different tastes, many different purposes, is something that has been made possible by the unique malleability, the unique control that is possible from this bottom-up approach. People build things in these worlds. In SimCity, they build simulated architectural systems, whole urban environments. But all of this is in the world of information and images. What are the prospects for taking that kind of technology, that kind of creative technology, and bringing it into the physical world? Well, we're beginning to see that, and we'll be hearing more about that today here at Tech Plus. That technology, of course, is 3D printing, where boxes, often ones that could sit on your desk, comparable in size to a paper printer, have machines that move precisely and put down small bits of material, not ink on an image, but bits of plastic, sometimes metal, to build out shapes. That technology has been used to make traditional objects. This was made by a 3D printer from a Japanese corporation. And also shapes of pure imagination. Here there is no spinning potter's wheel and shape of the potter's hand. What you see has more in common with computers and mathematics. And so 3D printing has given us a first taste of what it means to take the digital world and translate it into physical reality. I would like to ask you to imagine something more, something much more than that. And that something, well, here's the question. What if atoms could be arranged as easily as bits? In the information world, the smallest units of information are bits and bytes. In the physical world, the smallest units of matter are atoms and molecules. We use nanoscale components in huge arrays in integrated circuits to process bits and make the patterns that underlie the information revolution. What are the prospects for doing something similar, using machines to move the smallest particles of matter and organize those? And that is the center of what I will be outlining. So I ask you to imagine 3D printing perfected. And by perfected, I mean making not just plastics and metals, but the ultimate materials, building up from atoms and molecules with broad range of control of the patterns, can make not only the kinds of materials that we have in the world every day for engineering, but supermaterials, materials like fracture-tough fibrous diamond composite, materials that are better electrical conductors, structures that are better for computation, the ultimate products, the ultimate materials allowed by physical law, or close to that, and with the ultimate precision, atomic precision. This is enough to enable one to get another factor of 1,000,000 in information technologies. And finally, I would like you to imagine that these capabilities are also fast and inexpensive. So the key technology that will make this possible, not today, not tomorrow, but the path is clear, the prospects are clear, is one based on nanoscale machinery. So we know about machinery in the macroscopic world. You have three-dimensional objects, things with size, shape, motion. And typical ones are things like gears, bearings, and motors. And so on the macroscopic scale, a scale of centimeters, we have devices like these. And it turns out that the laws of physics and principles of chemistry tell us that similar structures can be made at a scale of nanometers, in which the teeth of a gear are rows of atoms, in which the bearings are sliding interfaces, where there is this internal symmetries are such that there is a high least common multiple of the inner and outer rings, which turns out to make the potential energy function very smooth and flat, an almost ideal bearing with two surfaces simply pressed together with the right structure. And I think these images give some sense of how small machinery might be able to work with atoms and molecules. If the machines themselves are nanoscale, and atomically precise, it becomes possible to design devices that bind molecules, move them like a component in a factory, combine them, not with glue or rivets or welding, but instead by chemical bonding, and put those pieces together to make larger things. So that gives some picture of how one might be able to build from the bottom up, to build with molecules as building blocks. But I also spoke in terms of systems being fast. Well, why does that follow? Well, it's a matter of scaling. Just as in electronics, smaller devices can work at higher frequencies, similarly in the world of machines. Shown in biology, a large bird will flap its wings perhaps twice per second. A smaller bird, hummingbird, 10 times the frequency. A smaller flying organism, another factor of 10. 1/10 the size, 1/10 the distance, 1/10 the time, 10 times the frequency. That is the scaling law. Fundamental, basic, elementary, falls out of Newtonian mechanics and the way the universe is put together. Take that down to the micron scale, the frequencies rise to megahertz, and on a micron scale, one can build complex machines. I think any production engineer will tell you that if in your factory you could make your machines perform 1 million cycles per second, they would be enormously productive. So the prospect here is to have a technology based on very small, enormously productive devices in proportion to their size. So with these kinds of components and a scale factor of 1 million, the prospects are for a new kind of technology. Now, I should again emphasize a warning. These things are not yet available. Our ancestors started with stone, worked up through iron, blacksmithing to the Industrial Revolution, using tools to build better tools. We are starting with those, and the molecular sciences learning to build atomically precise structures of larger size and better materials, leading to these technologies. The path is clear. It will not take a long time historically, but it will take years and then more years. How long? Fast enough to matter greatly to our world in the early to middle 21st century is my expectation. So, to put these pieces together in a literal sense, we're very familiar with the idea that if you have mechanical devices, they can be put together to make systems of machinery, and systems of machinery in combination can be used to build factories. And so, gears, bearings, and motors, devices that move things, that make things. Well, the story is the same on the nanoscale. Similar shapes, similar motion patterns, similar machinery, similar systems. And this leaves a further question. How can one bridge the gap between very small things and very large? When people think in terms of nanotechnology, they think of small things. I've spoken in terms of changing the material foundations of civilization, of changing the kinds of things that we can make in the world in a very broad sense. Well, the answer there is fairly straightforward. If you can make large machines and very small machines, then machines can be made of intermediate sizes. If molecules can be put together to make small building blocks, then somewhat larger machines can put those together to make larger components. And those can be used to put together larger components and larger, and so on. 4 steps, 16 pieces. 30 steps, 1 billion. Continue that process, and there's a path that goes from molecules to macroscopic objects. Take 30 steps 2 more times, that's enough to span the distance between molecules and objects on the scale of a ton. How long does this take? Well, this is not magic, this is about machines. We can think about machines. You have machines that move at a certain speed. like a centimeter per second, a meter per second, in that range. Small ones operate at 1,000,000 times the frequency because they go many, many cycles at that speed in a given length of time. But if you have a layer of machines that are very small and working at high frequency and then larger and larger, and particles are moving at a uniform speed, then molecules enter, they move through some path, they're combined to make larger objects, they move through some path, larger, 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 and finally are put together at the other end. If they're moving at a centimeter per second through a system on a scale of meters in size, then the time required to go from an input of simple chemical compounds to an output that might be a laptop computer with 1 billion processor cores, or might be a piece of extraordinarily high performance hardware for aerospace systems, is going to be on the rough order of 1 centimeter per second, on the order of a meter, on the order of 100 seconds. Think how long it takes to go from simple chemicals, metals, and so on to a computer today. Think of how large the facilities are, the billion-dollar fabrication facilities that Samsung and others build. Now imagine being able to make something that has products that are orders of magnitude better. The processing time is minutes, and the machinery will sit on a desktop and produce its own mass and product in a matter of perhaps days. When I speak of radical abundance, that's what I mean by radical. Radically different materials, components, systems, products, made by radically different means in terms of costs, in terms of time, performance, and the nature of the industrial infrastructure. So, I'm asking you now to imagine, but I cannot imagine, a world in which the human race has these capabilities. A world in which the kind of revolution that we have seen in the information world is repeated in the macroscopic world. A world in which, just as we see in the information revolution, small devices, nanoscale devices working together at high frequencies, organizing patterns of simple structures, is paralleled by systems of machinery. We've seen this before. Physics and chemistry tell us that this is perfectly reasonable. There's nothing special at any point. It's familiar physics. It's the same textbook quality information required to describe these systems in physical engineering detail. But the consequences will be revolutionary. If we're able to arrange atoms as easily as bits, the information revolution goes much further, more pervasive, the ability to make extraordinarily high performance systems at a cost like that of paper or cardboard or carpeting. Any object could contain billions of processor cores, and the cost would not differ. Building on a larger scale, lightweight materials, high strength, fast production of components that snap together easily. Well, today you can have furniture and move it around in your home. The ability to build structures as easily as moving furniture is one that comes naturally from this level of technology. And that means an ability to make architecture as almost as mutable as what we see in computers today. An architect can draw pictures of a building, but the path from that picture to a physical building is long and expensive. In the future, that path can be much shorter for buildings and for everything else. Today, our access to air and space is very much limited by what can be made. The prospect here is for being able to make materials with something like 1/100th the mass per unit strength, much higher performance. the potential for access to space as easy as access to other continents today. Once upon a time, people dreamed of space as an open frontier. The reason that hasn't happened is a manufacturing problem. It is the cost and performance of the material products necessary to make the spacecraft. That will change. Well, these are nice prospects, but the world has urgent problems of economic development and the collision between human needs and, through industrial processes, the collision with the limits of the Earth. And that is why one of the most important applications will be applications to transforming energy supply, which can be done rapidly. The ability to produce high-performance photovoltaic cells, thin films, lightweight deployable arrays that can be unloaded across flat ground rapidly, will open the possibility to transform the material basis of our energy economy to renewables at a rate that is higher than would otherwise be foreseen, and that can go further than has been contemplated. We know why that is important. The world's climate is changing because of side effects of industrial technology, and with our industrial technology, we do not know how to reverse that process. CO2 levels have been climbing. All projections say they will continue. Change will continue to an unknown end. People talk about creativity in the 21st century. Well, many people look forward and they're not sure there will be a 21st century in the familiar sense. Well, why don't we do this? We put the CO2 into the atmosphere. Why not take it back out again? There's no physical problem. You can do it on a small scale in the laboratory if you want. Take CO2 out of the air and put it in a bottle. But the cost is too high. It's rather easy to calculate. We have an amount of CO2 in the atmosphere in a dilute gas. The thermodynamic work of compression to take that gas and compress it to liquid density and store it is about 10 to the 21st joules. That's 3 terawatts for 10 years. 3 terawatts is approximately the same as the total human electric power generation capacity worldwide today. Not affordable. To produce that much energy, to do the work to clean out the atmosphere would be in excess of $100 trillion. But it's a manufacturing problem. That cost can be reduced by a factor of perhaps 100. A post-industrial technology has the promise of undoing the damage that has been done by our industrial technologies and remaking not only the human world, but restoring the natural world. So there's nothing small about nanotechnology in terms of its applications. The prospect that I have outlined is nothing less than making, in effect, a new world through a new way to make things. I've spoken briefly, abstractly, generally. There is, of course, much more science and technology and physics and consequences, economic disruption, societal disruption, military balance of power. These are real concerns that must be addressed. And so, for more information, I will direct your attention to a new report, Nano Solutions for the 21st Century, which is available for download from Oxford University at the Oxford Martin School. I think that Google will find it rather easily. And so, for your time and attention, kamsahamnida.